Okay, so if you want to write stuff down, here is some stuff you can write down. I wouldn't worry about these dot points if I was you because they're on the OneNote and it's not actually that important, but it's a list of things that matrices are commonly used for. So a matrix in general is just an array of numbers. So it's a little bit like a spreadsheet. It's just got a set of cells and you put numbers into it. And the vectors we did in the first topic, vectors is a special type of matrix with a special meaning that we applied in a couple of different areas in that first topic. So matrices can be used for transformations of functions, which we will do, storage of data and computation, which is actually a topic coming up very soon in the Math General unit. So the Math General students, 2 of them are in here, will be studying matrices over the next few weeks or maybe early next term. So it's not in Math Methods, but it is in general, it is in Specialist. Can be used for solving systems linear equations, dominance matrices to look at who dominates in a competition, who's the better team, etc. Population predictions using Markov chains and Leslie matrices. Probability forecasting using Markov chains, and also cryptography has a strong matrix list. And they're just the ones that are commonly used in Math C or are mentioned in the specialist curriculum. There's lots and lots of matrix context. So I don't want to upset anybody. I'm worried I'm going to upset somebody.
How worried I'm going to upset someone? I'm there though.
Oh, what?
Well, if you hadn't been sitting there talking with Dylan about your exam, perhaps. How much you got to go? How much you got to go?
I just writing the investigation. Location for dot multiplication.
Okay, and resuming. So this is a matrix. This matrix is a 4x3 matrix. And so that's called the matrix order. You'll notice, so it's got a height of m and a width of n, and it's an m by n matrix. So when we talk about the matrix order, 4x3, we look at how many rows it has and then how many columns it has. The matrix is named. You can call it, give it a name. Commonly, we'll give it a capital letter name. That's usually what happens, but you don't have to. You can call it Bob or Jackie if you want to. We can also call elements in a matrix, and this is a common thing as well, that we have a name capital A, but an element or a cell reference will be A, and A43 will mean the 4th row. Oh, that's not 4-3, that's 4-1. I'll change that in a second. 4th row, first term. So let me just change that. That's now on the video. Great. I'll edit that out. There we go, 4-1. Every cell has to be filled. If it's a 4x3 matrix, every cell is filled, even 0 counts. Each value is called an element. That's basically the general premise of a matrix. That's what it looks like. Any questions on that? We'll see how far we get. I'm not sure how far we'll get today. Using a matrix to store data. Oh, whoa. So one of the things that a matrix can be used for is to store data. We're not going to go into too much detail with this, but if you get a contextual question, it might be a matrix that has dealt with data storage. Yes, I've picked 4 names from in here, which was a mistake when I come to teaching this class next year and have to change all the names, but I'll deal with that then. And I'm going to use this for my first example, but this is a really common usage, and I'm going to show you how this representing this data as a matrix can help us to do some calculations, but that will happen a little bit later on. So we might have some, in this case it's food van sales, and HD is hot dogs, burg is burgers, wraps is wraps. Pretty boring. S is the matrix name, and S for sales, and I've put the data into a matrix form there. So all I've really done here is I've taken away some of the context. But as long as I've got some definition of the context somewhere, I can go back to the context if I need to, but now I've got something numerical that I can do analysis of and I can do calculations from. So this other thing in red here is really important as well. A matrix is really important for our link between human mathematics and our use of computers. So we often will represent data in a matrix form or in a spreadsheet, and then that gives the computer an opportunity to do procedural tasks on that data and to do program tasks on it. Here's a question for you. What does the sum of each column represent?
Number of cells.
Of? Okay, so this is the total number of sales of hot dogs, total number of sales of burgers, total number of sales of wraps. What does this row sum? How many things Elzani sold, how many things Chris sold, how many things Adam sold, etc.
Yes, Chris.
Yes, Chris, you are hopeless. Okay. Example 1. Consider this map. Construct a matrix R that represents the number of direct connections between towns. I'm going to leave you that for a minute and then I'll do the example. So here's my solution. And you'll see in this solution that I've represented the connection between A and C. There's only one road that goes from A to C, and I've got a 1 in the A to C, but I've also got a 1 in the C to A. So by having this set up, what does this create within the matrix?
Reflection.
A reflection, a diagonal reflection, some repetition. So there's a diagonal reflection. You'll also notice here that the diagonal itself, this is called the main diagonal, the one that goes from top left to bottom right, has all zeros. Why is that the case?
Because you can't go from A to A.
So there's no roads from A to A or D to D, which doesn't make sense. There could be a road from A to A, I don't really know, maybe a tourist trail or something like that. But in this case, we're in a context where it probably doesn't make sense for there to be a road from A to A, and those contexts will come up a lot. So another one will be if you're looking at dominance matrices, and you're dealing with a round-robin competition, and so say the boys on this table are in a round-robin competition, and Chris is not going to play himself, but he will play everybody else, and you'll have a win-loss situation there. So we've got that set up, and of course this context also allows us to have a 2 here because there are 2 ways of getting from C to D, which could be possible in this context, but some contexts that won't be possible. So we've built a matrix to store that understanding. So are we happy with that? I'm going to come back to this example later on as well because doing things with this matrix means something. Right now, you can do simple sums though. You can sum the columns. 3.
Why is it not for A to D?
Sorry?
Why is it not from A to D?
Because there's no direct line.
Oh, yeah, there's no direct. But if you square this matrix, which we'll come to later, squaring the matrix will produce something really interesting in that respect. If I add up my D's, that sums to 3, the column of D's, and I go over here and D's got 3 roads that come into it and exit it. So there's important features to this matrix here. So here's some definitions. Might be, just give me a look. We'll go into some matrix arithmetic. Here's some definitions, and you might want to write this down. It's within the textbook, it's on here. I'll leave it up to you whether you want to write it down, but I'm going to talk through them and I will give you time to write it down. So some special matrices and definitions. We've talked about an element. It's just a single value in a matrix. The order of the matrix is the number of rows times the number of columns. A up here is a square matrix. So the number of rows equals the number of columns, and that's called a square matrix. And there's some properties that hold for square matrices that don't hold for the others, so that's important. A row matrix is a matrix with 1 row only, so you can see B. You don't get many row matrices, but you do get a lot of column matrices, and we've used those for vectors already. So a matrix with 1 column like C is a column matrix. Matrices can be equal, but to be equal, every element has to be equivalent to every other element. So it's actually ends up being pretty uncommon. You can have a 0 matrix. So if all the elements are 0, then it's the 0 matrix. And you can have, and we'll talk about this a little bit more, you can have the identity matrix. But an identity matrix is always a square matrix, and the diagonal, the leading diagonal, is full of 1s, and the rest of the matrix is 0. Does anybody understand what an identity is? You may have talked about it before, you might not have. I haven't talked to you about it. So an identity element, or an identity, is a value that doesn't change another value under a certain arithmetic. So in the number system, we have a multiplicative identity. Does anybody know what the multiplicative identity is for the number system? The value that doesn't change a number if you multiply by it? 1. So 1 is the multiplicative identity. And in the number system, we have an additive identity. Anybody know what the additive identity is? 0. If you add 0, it doesn't change the situation. So we have the same thing with identity matrices, and this is the multiplicative identity, which is the only identity that's important, so we just call it the identity. You could have an additive identity, which would just be a matrix full of zeros, but we don't really use it that much. So we'll talk about identity matrices more a little bit later on, but for now, there's that, and I'm going to just pause this video again. I might just talk to you about this very quickly first. When we come to arithmetic in terms of number, why do we multiply things the way we multiply them? Because multiplication, is it something that was invented or discovered?
Invented.
It's invented. Why did we invent multiplication to do that? Imagine this for a second. And this is something that's now not in your curriculum, but it was in the old Maths C curriculum. Imagine if I had something like this. 7, this is just a symbol, so I could do 7 times 2 equals 16. So I said that, and I've just invented a new multiplication method, and instead of doing 7 times 2, 7 groups of 2, I'm actually saying, well, what I'm going to do is I'm going to do 7 times 2 plus an additional 2 is the way that I'm going to multiply from now on.
So it's actually 18.
7 times 2 is 14.
It's 7 times 2. You just define a new multiplication.
Yep.
And you're using the same rule.
So now, what you're saying...
Well, no, the point I'm making is that multiplication symbol, is just humanly defined. And yes, I'm using multiplication within it. I could have written 7 plus 7 plus 2 if I wanted to. So that's not really the point. The point is we have defined that 7 times 2 equals 14 because we go back to an old grouping system. It's important to us to have a situation where if I come up to you and say, look, I've got 2 bags of stuff and they've each got 7 things in them, you know that that's grouping multiplication. So multiplication comes from your primary experience with grouping. And we define multiplication as that rule. Yes, that will be on the video. It's good.
There's going to be a lot more on the video. There's a whole roll there.
Well, I'll be finished soon, hopefully. So, can we get back on topic, please? Thanks. So multiplication is humanly defined, but it is defined in such a way that it's useful to us. Addition is the same. It's useful to add elements the way we do. It's not useful to come up with other things like the one I just invented. The point here is that when we get to addition within matrices, subtraction within matrices, and multiplication within matrices, we have to go back and say, how do we do that? Because it's not obvious how we do that, particularly when we get to multiplication. And I probably won't get to multiplication today, but it's something for you to think about, because when we get there, you'll see that multiplication in matrices is not what you expect it to be, whereas addition and subtraction is. So adding and subtracting and multiplying by a scalar works exactly as you expected, and I'm going to go through this one example, and then I'll probably just leave it there for the day. So if I was to add A and B, matrices A and B here, I would just simply do the addition of each element in its position. So it'd be 2, 7, 3, negative 3, plus 9, negative 3, 7, 8. And I'm overworking this a little bit, but that would equal 2 plus 9, 7 plus negative 3, 3 plus 7, and negative 3 plus 8. And that will equal 11, 4, 10, and 5. And that's pretty easy, and I'll never talk about that again.
The negative 3, are you doing it for example 2? Shouldn't it be negative 2?
Yeah.
Oh, yeah. Okay. I've just copied that down rather poorly. That's a transcription error, which is minus half a mark. There we go. Is that better? So that's addition. That should be really easy, unless you make a transcription error. And part B is 3 times matrix A, which is 3 times 2, 7, 3, negative 2. This also works as you would probably expect, and that is that you multiply every element by 3. So you get 6, 21, 9, and negative 6. That's scalar multiplication. So we've got addition, scalar multiplication, and very quickly a composite of the two, but instead of addition we've got subtraction, which works exactly as we'd expect again. I'll give myself a little bit more room. 3a is 3 times 2, 7, 3, negative 2. Minus 2b is 2 times 9, negative 3, 7, and 8 is equal to 6 minus 18, and then 21 plus 6, and then 9 minus 14, and then negative 6 minus 16, brackets stay there, and I get negative 12, 27, negative 5, negative 22. And that's my new resultant matrix. I'll move up for that. Yeah, pretty much like vectors, but their multiplication changes a bit. So, you know, and we did define that new multiplication for vectors as well. The dot product was different to what we might expect. Is that all right? Okay, cool. That's it. I'm probably going to leave it there. So just in terms of our identities, negative b is the same as negative 1 times b, a plus 0 is just a plus negative a is 0, and a plus negative 1 times a is also 0. They're just some little side notes that do pop up in the questions. So this is chapter something. Let me know. Chapter 17. And you've got about 8 minutes left. You can come and ask me questions, or you can have a look at 17a and start working on some of those questions.